In this example, we need to find the x-coordinate for the stationary points, and this is for the function that is described in y. Now, at the moment, you don't have to understand at all how I drew this function, but the thing that is essential for you to understand is, when am I going to have a stationary point? Now, a stationary point is when I draw a tangent to my curve and my tangent has a zero gradient. Now, if you take a look where I'm indicating over here, there is a tangent to my curve when x is minus 1, and there's a tangent to my curve over here somewhere between when x is 0 and x is 1. This value is actually when x is a fifth, but we're going to discover this by working this out algebraically. Basically, what I want to know is, what is the x coordinate going to be at these 2 points? In order to do this, I need to find my derivative, because the derivative, you'll remember, is the gradient of my tangent to my curve. So if I take a look at the function that has been given to me, the first thing that I need to know is, if I want to find the derivative, is this function written so that I can use either my power rule, my chain rule, or my product rule? The only thing that I need to change is that surd. So in other words, I'm going to write my function as x squared minus 1 for the first factor, and the second factor is 1 plus x all to the half. You can see that this function is a product. It's a product of 2 functions. The first function I'm going to call f of x, and the second function is g of x. Because I've got a product of functions, it means I'm going to have to find my derivative using the product rule. The second function, g of x, is actually a composite function. So when I do the derivative of g of x, I must use the chain rule as well. So that we don't forget any of the parts in finding our derivative, I'm going to write it down again, just so that we remember that all the parts of the expression are written down. Because you have to do a lot, it's very easy for you to forget a small piece of information, which obviously will give you an incorrect answer. So finding the derivative of this function y in the variable x, I'm going to find the derivative of the first factor and times that by the second factor. And then I'm going to find the derivative of the second factor, and I'm going to times that by the first factor. So for my y value, my y graph, I have the derivative of f of x is going to be 2x, and that must be times by g of x, which is 1 plus x all to the half. Now when I find the derivative of g of x, remember it's composite. So I find the derivative of the outer function times by the derivative of the inner function, which is 1, and I must still times that by f of x. Now if we go back and take a look at our diagram, remember I said to you that the derivative is the gradient of your tangent. Well, we can see at these 2 places over here, the derivative is going to be equal to 0. In both of these places, I can make my derivative equal to 0, and that way I should be able to solve to find the x-coordinate at the stationary points. Now that I know that I can find the x-coordinates of my stationary points, if my derivative is equal to 0, I'm going to take this answer for the derivative of y, and I'm going to make that all equal to 0. I'm going to write it so that all the factors that had positive exponents stay in the numerator, but the factors that had negative exponents go into the denominator. So in the second term, I actually have to write everything all over the 2 factors of 2 and 1 plus x all to the half in the denominator. And that whole expression is now going to be equal to 0. I'm now ready to solve for x. When I want to solve for x, I must first use the LCD to get rid of the denominator. The LCD in this equation is going to be 2 and then the bracket 1 plus x all to the half. Remember that we use the LCD in the equation to get rid of our denominator, and so the first fraction that didn't have either of those factors must get those factors times by its old numerator. So its new numerator is now going to be 4x. Now, if I have 1 plus x to the half and I times it by another 1 plus x to the half, I've actually got 1 plus x to the 1. The second term had all those factors, and so I'm just left with x squared minus 1. And then if I times 0 by all those factors in my LCD, 0 times anything is still 0. Immediately you can see that this is starting to look a little bit easier. Now there are many ways that you can progress. I'm going to show you how I'm going to do a difference of 2 squares in the second term and take out a bracket factor of x plus 1. So in my next step, I have 4x. I'm going to write that so that it's x plus 1, so that I can recognize that I have a reducing degree of x in all the brackets. Doing the difference of 2 squares, I get x plus 1 and x minus 1, and that's still all equal to 0. Now taking x plus 1 out as a common factor, I'm left with 4x plus x minus 1 in my second factor. Simplifying the second factor, I've got x plus 1 and then 3x minus 1 equals 0. Sorry, that's not 3x, 5x. And so if I make each factor equal to 0, I'm going to have x plus 1 equals 0, which means that x is equal to minus 1. Or if 5x minus 1 is equal to 0, x is equal to 1 all over 5. So without considering my restrictions, we can see that the gradient of the tangent looks like it is going to be 0 when x is minus 1 or when x is 1 over 5. Go back now, though, to the first part of your equation for the gradient of the tangent. And can you see that because you've got a factor in your LCD which has a restriction, because your factor can not be 0 when I have 1 plus x to the half is equal to 0. In other words, my restriction is when x is equal to minus 1. This means that I shouldn't be able to find a tangent, which is a horizontal line, when x is minus 1. Now we assumed this in our diagram above. I'm going to take you into AutoGraph now to show you that this is not actually the case. In other words, there is going to only be one place on this graph where my gradient of my tangent is going to be 0, and that will be when x is going to be equal to 1 over 5. Here we have the diagram that I gave you earlier, and this is the diagram of the function we represented in y. What I've done here now is I've highlighted when x is minus 1, and using AutoGraph I'm going to draw in the tangent. When I draw this tangent in, you can see clearly that that tangent does not have a 0 gradient. In other words, we only had one tangent which had a 0 gradient, and this is the tangent when x was going to be equal to 1 all over 5.